and we'll go from current slide. I assume we will. Here we go. Now, any questions on anything? There were a few questions on the quiz before I came in. Did you get that? Was that satisfactorily answered? I wanted to make sure it was out there. Any others? Was that a stretch? Okay, stretch. Okay. All right. No other questions? All right. There probably will still be people coming in, hopefully, as class goes on. What does rational mean? And it's not gender related, by the way. Never mind. No, I didn't say that. Okay. What does rational mean? Ratio. What does a ratio? Division. Exactly. One number to another. Okay. All right.
Corner.
Yeah, I know. I'm trying to find you. There you are. Okay. Jalen. Okay. All right. Now, it refers to ratios. Okay? And what we're going to be doing here is this. The rational zero test. Remember what this section is focusing on is we've got to find the zeros for these polynomial functions. They were easy, relatively, when you had quadratic functions. Yeah, you could either factor or use a quadratic formula, or you may find there's no zeros at all. Now, with higher order functions, there aren't any easy rules like that. So we need to come up with a way to find those zeros. Here's one. This only works for rational zeros. These are zeros that are rational numbers. Irrational numbers, you're not going to find them this way. Complex numbers, certainly you're not going to find them this way. Only for rational numbers, but that will give you a fair amount of your zeros. Okay? It relates to the possible rational zeros of a polynomial. Now, these polynomials have to have integral coefficients. You can't have polynomials with, you remember, to define a polynomial, the coefficient can be any real number. Okay? Please. Huh? Ebony, got it. Just finding you as there you are. Okay, and Josh. There you are. Okay. Now, remember when we first defined what a polynomial function was, the requirement, the exponents had to be positive whole numbers. If they're not a polynomial. But we said the coefficients could be any real number, except that first one can't be zero. Okay. Now, that's true for polynomials in general. But we're dealing with the rational zeros test, and this only works for polynomials having integral coefficients. That means you can't have fractional coefficients, you can't have decimal coefficients, you can't have irrational coefficients. Okay? And you certainly can't have complex coefficients. You have to have strictly integers, plus or minus whole numbers. To the having integral coefficients is the sentence is rather weird. Relates the possible rational zeros to the leading coefficient and to the constant term of the polynomial. So here's your polynomial. F of x, base of n, x to the n plus a to the n minus 1, x to the n minus 1, plus dot, 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 all the way up to a2, x squared, a sub 1, x, plus a sub 0. Okay? Before, these coefficients could be any real numbers. Now we're limiting them to integers, plus or minus whole numbers, every one of those a's. Okay? Now, how we investigate what the possible zeros are, we're only going to use this one and that one. These in the middle, not going to mess with. Just the first and the last. The initial, the leading coefficient, and the constant coefficient. Okay, constant term. Okay, and here's what we do. Every rational zero of this polynomial with integral coefficients will have to have the form of P over Q. Of course, P over Q is a ratio of two integers, yeah, where P and Q have no common factors other than 1, And P is a factor of the ace of 0, and Q is a factor of the ace of n. Okay? Now this is a lot of blah, 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 and I don't know if that makes a lot of sense to you now, but once you do them, I think it'll start making more sense. But a few more blah, blah, blahs first. To use the rational zeros test, you should first list all the rational numbers whose numerators are factors of the constant term. The denominators are factors of the leading coefficient. And I'll show you how to do this in just a minute. So in other words, your possible rational zeros are all the possible factors of your constant term divided by all the possible factors of the leading coefficient. Now, having formed that list of possibilities of rational zeros, then we use a trial and error approach. It's almost like factoring method to determine if any of the actual zeros are actual zeros of the polynomial. But it's not just random trial and error. There's a system to it. Note that when the leading coefficient is 1, that makes it really easy. Only factors for 1 are plus or minus 1, okay? So that makes it really easy. So then the possible rational zeros are all not ratios anymore, well, over 1. They are the factors of the constant term. That's all. So let's do one, okay? Now, again, all those words were mostly words. Let's find the rational zeros of f of x equal x to the 4th. Whoa, this is example 3. Let's first do example 2, okay? All right, now let me see how I'll do it here. All right, let's first do example 2. Find, if possible, the rational zeros of f of x equal to x cubed plus x plus 1. Now this one's fairly easy to find the possibilities. Okay? All your rational zeros are going to be of the form p over q, where p is what? All the possible factors of the constant term, which is 1. What are the possible factors of 1? Plus or minus 1. Okay? Really easy here. And q is all the possible factors of what? The leading coefficient, which is 1. So that's plus or minus 1. So all your possible zeros are strictly plus or minus 1. That's all, folks. Now, how do we check to see if this is a real zero? Say again? Okay. That is the best way to do a plus 1. And guess what? Plus 1 is always a possibility, so plug it in. What would be f of 1 then? Oh, yeah, okay, you add it on. 1 plus 1 plus 1, right, which is 3. That's not 0, right? Everybody agreed? Okay. Now, you could plug in the minus 1, okay? And that's pretty easy to do. F of minus 1, and what would that be? Negative 1 minus 1 plus 1, and guess what that is? Negative 1. Guess what? There are no rational zeros for this polynomial. But what we do know, it is a number somewhere between plus 1 and minus 1 because, is not 0. Okay, this is equal to 3. Let me go and make that a little bit nicer. Okay, I got the talking faster than I could write. It's not working. Okay, there we go. Okay, this is equal to, I did it again, equal to 3, which is not equal to 0. And of course, negative 1 is not equal to 0. But because of our intermediate value theorem, we know the real 0 has to be between plus 1 and minus 1. Okay? Now, there is a number between plus 1 and minus 1, a real easy one. Okay, let's plug in a 0 here. Alpha 0 is what? Say that again. Yeah, 0 plus 0 plus 1, which is equal to 1, and that also is not equal to 0. So now we've narrowed it down. We know that your real 0 has be between 0 and minus 1. At least one real 0 is there, but we don't know what it is. Rational zeros test will not give it to you. Okay? So, it's not possible to find it that way. So what we do is, this is a bit bizarre too. It's not a rational number, and therefore it has to be an irrational number because you know it's real. And usually, I'm sorry. With a square, if that was a square, then that would always come in a conjugate pair. This is a cubic function, so it doesn't necessarily. So it's some number between 0 and 1, 0 and negative 1, and that's all we can do on that one. Okay? There are no rational zeros. So that may be why they left that off of the slideshow. So let's clear that, and now let's do this one. Now that we got our feet wet for it, what would be the form of all your rational zeros here? Rational ratio of P over Q, where P is what? All the possible factors of negative 6. What are the possible factors of negative 6? Plus or minus 1, what do you say? Plus or minus 2, plus or minus 3, and one more, plus or minus 6. Okay? I should have taken more room. And what's the denominator? Your Q. Plus or minus 1. Now this is one of those cases where your denominator, your leading coefficient is 1, so all the rational zeros have to be one of those numerators. You won't have any fractional forms of rational zeros. Okay? Now, again, what you did before, not a bad idea. Plug in a 1. That's the easiest way to sample to see if 1 is a rational zero. So let's do alpha of 1. What will that be? Say again. 1 minus 1 plus 1 minus 3 times 1 is 3 minus 6. That's why it's so easy to do. All you do is put down the coefficients. 1 minus 1 plus 1 minus 3 plus minus 6. Add those together, you get a 0? No, you don't. Okay. It's easy to check 1. It doesn't give you a rational 0, so then the next easiest one to check is probably going to be your minus 1. Now, to me, plugging in a minus 1 is not bad, but there is an easier way. We just did it. Anyone remember? Say again? It's what Jacob's question was earlier, related to it. If you do synthetic division, okay, then if you get a remainder, it's not a factor. If you get a 0, it is a factor. And synthetic division, remember, is really easy. Maybe not quite as easy as adding coefficients, but it's easier than, well, it's still pretty easy. So let's do this time. Now, here's the difference with synthetic division. If we're trying it as a solution, we put the minus 1 out there. You don't change the sign of it. If it's x plus 1, that would give you x equal minus 1. So you change the sign if it's a factor, you don't change the sign if it's a solution. What do we put inside the house? Though we don't have a house here. 1, negative 1, 1, negative 3, negative 6. And what check do I usually tell you to do? Count how many numbers. 1, 2, 3, 4, 5. What's your degree? 4. Yep, that's good. The number of numbers there has to be one more than your degree. If it's not, you're missing a 0 somewhere. Okay, then what's the next rule? Skip a line, draw a line. Okay, then bring down the 1. You tell me what to do, huh? And what you get? Negative 1, negative 2, two, 3, negative 3, negative 6, 6, 0. Ding, 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 ding. We have a winner. We have a winner. We have a 0 for that polynomial is x equal negative 1. Okay. Now, that may have been maybe a little harder than plugging in minus 1 and checking, but guess what? If you had done that, your next step would be do synthetic division, because you want to know what the other factor is, and here it is. Now here's something else you've got to do. Remember, you may have repeated zeros. So once you've done negative 1, you know 1 doesn't work, so don't mess with 1. Let's do negative 1 again and see if that's 1. If it's a repeated 0, minus 1. What you do? Skip a line, draw a line. Help me, help me. Bring down the 1. Come on, y'all know it. Multiply, and what does that give you? Negative 1. Say again. Negative 3. Multiply, that gives you positive 3. Add, you get 6. You get negative 6. Bing, not a 0. Had to have a remainder of 0. So negative 1 is a 0, but it's not a repeated 0. So what we do, we erase this stuff. It's easy for me because I have a magic pen. But we're not going to do negative 1 again. Negative 1 is a 0. So let's just write that down. It said find the rational zeros. Here's 1. X equals minus 1. Okay? So what do we do next? We go for the next possibility. What you want to try? We eliminated 1. We found negative 1 worked once. So what do we try next? 2. Okay? Let's try 2. So let's put a 2 on the outside. Skip a line, draw a line. Bring down the 1. Tell me what to do. Say again. Multiply. That'll give you 2. 0. Second. And what you get? 0. 3. 6. 0. Ding, ding, ding. We've got another one. Okay? X equal 2 is also a 0. Okay, we found 2 zeros now. What might you try next? No more synthetic division. Why? You're down to 3 terms. What does this 3 terms represent? A quadratic. X squared plus 3. Okay? That's a quadratic. So we write that down. X squared plus 3. We set that equal to 0. You think we're going to come up with anything? You think we're going to come up with anything? Do you think we're going to come up with anything? Do you think we're going to come up with anything? Okay. Say again? It's not factorable. And there's no real zeros. You have found the only two, x equals minus 1, x equals plus 2. Now remember what we did in the last section, which was, I said you're not really responsible for. What this tells you, the remaining two zeros are complex with imaginary components. That would be plus or minus square root of 3 times I, okay? Or I root 3, plus or minus I root 3. No rational zeros. Those are your only two. Your last two, remember fundamental theorem of algebra says you're going to have 4 zeros. 2 of them are complex, 2 of them are rational. In fact, 2 of them are integers. See how it works? All right, good deal. So it's not too bad, okay? You don't need to try any of the rest of them, okay? You got down to a quadratic. It's not factorable. You can't even do quadratic formula on it because you're going, well, you can, but you're going to get imaginary parts of your solution. Okay, so that's all you needed. The rational zeros were minus 1 and plus 2. Now, what else can you do? You can factor this thing now. This factors as f of x. This thing factors as, if x is equal to negative 1, the factor is what? X plus 1. Just add 1 to both sides, x plus 1. And if the factor is, if the 0 is 2, x equal 2, what's the factor? X minus 2. And then your last factor is x squared plus 3. You have factored it as far as you can factor it. So not only does this give you your rational zeros, it gives you possible factors, and then whatever you end up with, that's your last factor. Okay? So you not only have, and what, before, were we able to factor a 5-term 4th degree polynomial? No way. Okay? Not even by grouping, because you have to have an even number of terms in the group. So now we have a way to factor a 5-term 4th order polynomial. So this has opened up lots of possibilities for us. Okay? That's how I did it. Let's see how they did it. Okay, we'll erase all the ink. And what they do first, because the leading coefficient is 1, the possible rational zeros are your rational factors of 6. Plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay? Now you know you can't have more than 4 zeros. Fundamental theorem of algebra, right? Okay? So therefore, we're not going to use all 8 of those. We know that. But we're going to start with the small ones because they're easy. And let's go to town with it. They don't show you the early steps. First try 1, it didn't work. Try negative 1 by synthetic division, and sure enough, it works. Okay? Then you didn't have to write it down again. You could have just done 2 here. But it's always a good idea to do negative 1 again to see if you have any repeated zeros. Okay? You didn't, so you tried the next one, which is 2. That gave you a 0. Stop there because this is a quadratic. You can evaluate that from what you got. X squared plus 3 equals 0, not in the real number system. Okay? So x equal 2 is the 0. And so the factors are, and they didn't ask you for factors, did they? They said, what are the rational zeros? But the factors are, because x equal minus 1 is a factor, add 1 to both sides, you get x plus 1 is a factor. Because x equal 2 is a 0, subtract 2 from both sides, you get x minus 2 is a factor. And then what you have left over here, x squared plus 3, you can't factor that. That's your last factor. Okay? Make sense? All right. Good deal. Let's see. Oh, yeah. They're going to show us the graph, too. Here was x equal negative 1. Here was x equal 2. And What other point on this graph would be real easy to plot? Say again? 0, negative 6, the y-intercept, with x in 0 in for x, and then that 0, that 0, that 0, that 0, y is equal to negative 6. And sure enough, there it crosses at 0, negative 6. Okay? Now, in behavior tells you it's on the up and up, right? We know a lot about this function. Okay? There's no more zeros, so we don't know if it does anything else. Plot it using a plotting device or something else. You'll see this is how it turns out. No more real zeros. No more rational zeros. Okay. Good deal. Any questions? All right. When the leading coefficient of a polynomial is not 1, the list of possible rational zeros can increase dramatically, because now you have denominators as well. Okay? In such cases, the search can be shortened in several ways. Now, they say a programmable calculator in your book it says a graphing utility. Okay? Whichever can be used to speed up the calculations. That makes things go faster. But if it's graphing, draw the graph, okay, either by hand or with the graphing utility. It gives you an estimate of the location of the zeros, okay? And then, like I said before, the intermediate value theorem, along with a table generated by the graphing utility, can give you approximations of zeros, okay, if there are any more, okay? Now, your book lists one more, and that synthetic division can be used. Let's see if that's on the next. Oh, yeah, there it is. And synthetic division can be used to test the possible rational zeros. I would put that near number 1, okay? That's probably the easiest and best thing to do. Finding that first zero is often the most difficult part. After that, the search is simplified because you're working with smaller and smaller polynomials. How small do you get before you stop? 3 terms, which is a quadratic. Because a quadratic, you can analyze by itself. Okay? Working with lower, okay. And example 3 shows that you just keep doing synthetic division with the smaller and smaller. Once you find the zero, recall that if x equal a is a 0, this is what we just did, then what's the function? I mean, what's the factor? X minus a, exactly. Then x equal a is also a solution to the polynomial of f of x equals 0, and x minus a is a 0, and a0 is an x-intercept. All those things are true if x equal a is a 0, or a solution, x minus a is a factor, or a0 is a intercept, x-intercept. All right. Now, that was example 3. Okay, they're skipping example 4 and 5, so let's go back and do them here. Okay, this is going to give us the most room to work. So here's example 4. Find the rational zeros of f of x is equal to 2x cubed plus 3x squared minus 8x plus 3. All right? Where would you begin? Okay. You're looking for a p over q, where p is all the possible factors of 3, which are plus or minus 1 and plus or minus 3. And your denominator is plus or minus 1 and plus or minus 2. So let's start listing them. We didn't have to list before. We had 1 in the denominator. This one time we do. And I like to start with the whole numbers because I like whole numbers better, okay? So that's going to be, your possible rational zeros are going to be plus or minus 1 and plus or minus 3. Now let's start using the denominators. Well, we just used them because over 1. So the other would be plus or minus 1 over 2, plus or minus 1/2, and the last one would be plus or minus 3/2. Very good. I'm going to save those till the end, hoping we don't have to get there. Okay, which one is going to be the easiest to test first? 1. And how do we test it? Say it again. Okay, just add your coefficients. 2 and 3 minus 8 is plus 3, 0. Okay, so we know x equal 1 is a 0. Okay. However, you know what the next step is going to be? Synthetic division. Okay, you know it's a 0, but you need to know what the rest of the factors are. So put the 1 on the outside, and what do you put on the inside? 2, 3, negative 8, and 3. Do we have enough numbers there? 4, and what's your degree? 3. Yes, you have enough numbers. So what's your next step? Skip a line, draw a line. Don't forget my little step there. And then bring down the 2. You carry on from there. 2, 5, 5, negative 3, negative 3, 0. You knew that was going to happen. You'd already plugged it in. What are you down to now? A quadratic. Don't do any more synthetic division. Write down, what is that quadratic factor? 2x squared plus 5x minus 3. Set that equal to 0. We're looking for the zeros, right? And then what do we try to do? Factor, okay? All right. Now, what's the only possible factorization of 2x squared? 2x times x. Where do we look next? Sign of the last term is negative. That means these two have to be 1 negative, 1 positive. You want them in that order? Negative, positive. What's the only possible factorization of 3? 3 and 1. In that order? Let's try it. 3 and 1. Okay? Let's pull it and see if we did it right. 2x times x is 2x squared. That's good. 2x times that would be a 2x. Minus 3x is negative x. Right? Don't make it do what you don't want. Okay. It's negative x. Wrong number. So therefore, we better change our numbers. If it's just the wrong sign, then we change our signs. But these are wrong numbers, so I'm going to put the 1 here and the 3 there. Okay? So we'll put the 1 here and 3 there. Now let's try our formula. 2x times x is 2x squared plus 6x minus x plus 5x minus 3. Yes, we've done the factorization. And guess what? What would be the zeros? 1/2. There it was. Where was it? Right there. Positive 1/2. And what's the other one? Negative 3. There it was. So yeah, we identified them all. We didn't have to find them all by synthetic division. Get it down to your quadratic, then try to factor. Okay? So, let's, find the zeros. You just told me what they were. What's the second one? 1/2. And the third one is, yuck. I say 1/2 and write 1/3 because I was saying, and the third one is, okay? And the other one was negative 3. There's your 3 zeros. That's all you can have because it's a third degree polynomial. Can't have any more than 3. We found them. There they are. Good team. Way to work. We also have the factorization. What is the factorization for this polynomial here? What's the factorization? Well, you got two of them right there, right? 2x minus 1 times x plus 3. What's the third one? X minus 1. Very good. There's the factorization of that. So we just factored a cubic polynomial. You couldn't do it by grouping. Won't work by grouping. You could try grouping, but it's not going to give you the answer you want. So we just factored a cubic function that we couldn't before. Thank you, synthetic division. Thank you, rational zeros test. We now have more tools in our belt to come up with factoring or solutions. They go hand in hand. All right, so that was example 4. Let's see what they got in the book. X equal 1, x equal 1/2, and x equal -3. Good for them. Okay. And by the way, folks, every one of these examples in the book has a checkpoint. Please go and do the checkpoints as soon as you can after class to make sure you remember how we did it in class. Okay? Want to do 5? Sure we do. Okay? All right, example 5. Find all the real solutions, okay? They're not asking for rational anymore of this one. This is an equation. Solutions they're asking for. -10x cubed plus 15x squared plus 16x minus 12 equals 0. Okay? We're looking for all the real solutions for that. Now, where would you typically start? Say again? Where would you typically start? See if there are any common factors. Are there? Well, that's promising. This is 2 times 5, that's 3 times 5, so 5's are common, but it's not common to the other two. So no, there aren't any common factors. Boo hiss. I was hoping to make those numbers smaller. Can't do it. 3 of them are even, but 1 of them's odd. Can't do it 2. Nothing common, so where do we try next? What? Okay, the rational zeros test. Okay, the rational zero test will be of the form P over Q, where P is, all the possible factors for 12. And you don't worry about the sign because you're going to put plus or minus anyway. So what are the possible factors of 12? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Wow. Whole bunch of numerators there. This could take a while, huh, folks? Not really. What's your denominators? Plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Oh, this could take a while. Maybe. Okay? Yes. Oh, were you just stretching? You get that from the leading term, leading coefficient. All the possible factors of the leading coefficient. The numerator is all the possible factors of the constant term, and the denominator is all the possible factors of the leading term. What's that? Yeah, 10, 15, 16. It's -10, 15, 16, and -12. Right. Okay. Now, what is the easiest? Okay, let's list all those possible zeros. We'll be here a while, okay? I like to start with them over 1. That just gives you some numerators. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, now let's start with the fractions. What are they? Plus or minus 1 over 2? That would be, you tell me. Okay. What I did there to get these, I did all these numerators over 1. Okay, that's just going to be that. Plus or minus 1, plus or minus 3, plus, Okay. Now, we do all these numerators over 2. What will they be? Plus or minus, what do you say? 1 over 2, 1 half. Okay, we've already listed one. You don't have to list those anymore. Thank you very much. Okay. Next, plus or minus 3 over 2. Next. Already got 2, so you can skip 4 over 2. You already got 3, you can skip 6 over 2. And you already got 6, you can skip 12 over 2. So, it's, huh? You see what you're doing? Okay. You're doing, okay, to get these, you did all these over 1. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. That's those. Then you did plus or minus 1 over 2, which is 1 half. 2 over 2 is 1. You already got that. Don't write it again. Then you do 3 over 2. There it is. 4 over 2, well, that's 2. You've already got that one. 6 over 2, 3. You've already got that one. And 12 over 2, that's 6. You already got that one. So you don't have to list those again. So what's next? Yes, and that would be 1 over 5, 2 over 5, plus or minus 3 over 5, plus or minus 4 over 5. There is no 1. That's a 6 over 5. You got to put that one too. Plus or minus 6 over 5 and plus or minus 12 over 5. Okay? Whew. And you're not through yet. You still got 10 to go. Okay? And what will that be? Plus or minus 1 over 10. Plus or minus 2 over 10 is 1 over 5. You already got that one. Good, thank you. Next, plus or minus 3 over 10. 4 over 10 is 2 over 5. You already got that one. 6 over 10 is 3 over 5. You already got that one. And 12 over 10 is 6 over 5. You already got that one. There's your possible zeros. We could be here a while. But what's the easiest one to do? 1. How do we do 1? Say again? Plug it in. Add your coefficients. Okay? So let's add the negatives. Minus 10 and minus 12 are minus 22. Plus 15 and plus 16 and 31. 1's not going to work. Guess what that does for you? You don't have to try 1 with synthetic division. You already know it doesn't work. But minus 1 might. So let's try minus 1. And here I would go with synthetic division. So minus 1 on the outside, what goes on the inside? Negative 10, 15, 16, negative 12. Do we have enough terms there? Yes, 4 terms, degree is 3, perfect. Then you do what? Skip a line, draw a line. Then you bring down the negative 10. Then you multiply, and that gives you 10, 25, sorry. Multiply, negative 25, add, negative 9, multiply, ain't gonna work, is it? Okay? Hang up negative 1, okay? So, we're gonna erase this, and that. All right, now, we already tried plus 1, it didn't work, minus 1, it didn't work, both of those are gone. Now I like to go for the integers first because they're a little easier, and I'm lazy, okay? So I'm going to erase this. Which one you want to try next? 2? Let's try 2. I already skipped line, drill line, and break down my minus 10. So what do you go from there? Negative 20, negative 5, negative 10, 6. Oh, ding, 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 12. We got a 0, folks. Okay? So what did it ask for? It asked for the real solutions. This is a solution. X equal to is a real solution. What do we do next? See, we didn't have to do any of those fractions. Thank you very much. But, what is this? Okay, this is a three-term quadratic. Let's write it down. That'll be negative 10 x squared. Continue. Continue. Negative 5x plus 6. Let's see if we can factor that baby, because this is still equal to 0, right? That was our original problem. So let's see if we can factor that. Whoa, a lot of possible factors here. Okay, what you want to try for negative 10? You know what? I really don't like starting with a minus sign. And since this is an equation, I can multiply everything by minus 1, and that's still the same equation, right? Okay, I like factoring that one a little bit better, because this is an equation. If it's a function, you can't do that. This is an equation. Multiply minus 1 by 0, you still get 0. Okay? These will have the same factors. Now, what one do you want to try? Factors of 10. I sort of like 5 and what? 5 and 2. So let's make it 5x and 2x. Okay? Now, what factor? Okay, then next you look at the sign of the last term, which is negative. That tells you these are negative 5. So let's do it in that order just to see if it worked. Minus plus. Okay? What's the, you got several possibilities for 6. What you want to try first? Second? 3 and 2. Okay, let's try. I'm not going to do 3 and 2. Because, you see, if this were a 2 here, that would have a factor of 2. If that had a factor of 2, this would have a factor of 2. It can't have a factor of 2. So I'm not going to do 3, 2. I might do 2, 3. Okay? That would be a possibility. Okay? Let's pull it and see if that works. 5x times 2x is 10x squared. That works. This will give, again, 15x. Minus 4x is not going to be 5. Okay, that's going to be 11x. So the number's wrong. Can we switch numbers? Not really, unless we change to make it 6. But you know, since this is a small number here, by switching and making bigger numbers here, one of the other places you're going to make this number bigger. I'm convinced this isn't going to factor. I may be wrong, but I don't see how it's going to factor. So if it doesn't factor, what can we use? If it doesn't factor, what can we use? Starts with quadratic. Formula, that's it. Okay. Too bad tests won't have hints like that, will they? Okay. So let's do the quadratic formula. I wish I had more room. And since we've already got our 0, x equal 2, I'm going to erase this and do my quadratic formula here. Okay? I don't need that anymore, I don't think. I might, but I'll come back to it if I need it. That didn't work, so I'm going to erase it too. I do want to keep that because I need those coefficients to do the quadratic formula. Someone remind me how to do the quadratic formula. Wait, okay. X equal. Now let's see. Do we need to go back to the original? I don't think so. Yeah, what?
Of that 10x squared plus 5x minus 6?
Yeah.
It would be 10x squared plus 5x. And then you have to half 5.
Okay, you're doing completing the square. which is another technique. But I thought we so disliked that we thought once we got the quadratic formula, we'd never use it again unless we had to. Okay, so what does the quadratic formula look like? We got it through that same technique you said. Okay, say that again. It's minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay? Write that down and bring it with you to any test if you need to. What do we do next? Plug it in, but what do we plug? Okay, so the b is 5, so that would be negative 5 plus or minus the square root of 5 squared, which is 25. Now, I count minus signs next. I have a minus here. A is positive, but C is negative, so that's going to be plus. Good deal, folks. And what's 4 times 40 times 6 is 240. All divided by, well, 20. All right, 2a, 2 times 10. All right, we got some work ahead of us here, okay? Minus 5 plus or minus the square root of, what's 25 plus 240? 265 divided by 20. Now, someone with a calculator, see if 265 is a perfect square. I think not. It's not. So, let's see if it'll factor any. I know 5 will go into it. Okay? 5 will go into 26 5 times. 5 will go into 15 1 times. That's 51. And that's 3 times 17. So there's not going to be any factors. There's your answer. Okay? These are your last two real zeros. X equal minus 5 plus or minus the square root of 265 divided by 20. Okay? And that's exactly what they got here. They wrote them separately. Now, they did do something a little differently in that they used the original function we had, which was a minus, minus, plus. But guess what? It gives you the same solution. They just did a plus here and a minus here, and that's still a plus or minus the square root, so it's going to give you the same two answers. Okay? So it doesn't really matter which way you write it. I like this way a little better. So those are your last two zeros. X equal 2 is your rational zero. These two are irrational zeros. Still real, just irrational. Okay? Good deal. There's a checkpoint. Guess what? Recommend you do that. And I also sadly say, we're almost out of time. Okay. Get over it, people. Okay. All right. We'll start next time with conjugate pairs. Okay. Now, we're just going to sort of zoom our way through this because there was nothing in our course description that said we needed to deal with complex numbers. But I'll show you what we do with complex numbers. But by the way, that one we just had, that was a conjugate pair. Minus 5 plus or minus the square root, so that was a conjugate pair. Okay? It was just irrational conjugate pairs. Here they talk about complex conjugates. Let me give you a few homework assignments. I know you want those. You wouldn't want to leave without them. I know you wouldn't. Okay? You can do any of the odds 9 through 13. 9 is on CalcChat and CalcView.com. The others are on only CalcChat. Do either 15 or 17 or both. They're CalcChat but not CalcView. Do any of the odds 19 to 27. All those are on CalcChat. 25 is on CalcView. Do either 29 or 31 or both. 29 is on CalcView and CalcChat. 31 is only on CalcChat. And do either 33 or 35 or both. They're both on chat but not on calc view. Either 37 or 39. Let's see. And they're on calc chat but not calc view. And then stop right there. In fact, some of those others may have imaginary parts. If they do, you can just ignore them. Just forget those and go on to another problem. I know the next group are all going to have imaginary parts, so we'll do those next time. Good deal. Huh? Stop at 39, yeah. And some of those you might not be able to do if they have imaginary numbers. Just hang on to those. We'll talk about those later. What's that? Oh, I thought you said something.
Just have a good one.
All right, you too. Have a good weekend, everybody. Working math will make it good, right? Of course it will. Okay.